Okay, chapter 3 starts with 3.1 radicals, which is a bit strange that we have this section here because it's a lot of review from grade 11. It's also quite a bit of review from chapter 1. So, let's get going. And I think you'll see that you know a lot of this stuff. First thing I'll do is just remind you of some terms. So this sign here is called the radical sign. The number inside is called the radicand. And the number out front, the little number up top, is called the index. Okay, fourth root of 16, that equals 2. Why? Because 2 times 2 times 2 times 2 equals 16. Now, you might say, yeah, but doesn't negative 2 times negative 2 times negative 2 times negative 2 also equal 16? And the answer is yes, it does. But when we're evaluating, like these questions, we're not solving anything, we're just evaluating. And when we evaluate, we always take the principal root. Principal root. And the principal root is the positive one. Now this is for even indices, even index. For an even index or for even indices, that's indices. For even indices, only the principal root is what you take. Okay, so next question. Fourth root of negative 16. Can't do it, right? Because positive 2 times 2 times 2 times 2 is 16. Negative 2 times negative 2 is also 16. It's impossible to get negative 16. So this is no solution. In fact, this is always going to be the case if you have an even index. Then the amount inside here must be positive. What about an odd index? Well, the cube root of 27 is 3, because 3 times 3 times 3. Can we take the cube root of a negative? Yeah, that's fine. It's negative 3, because negative 3 times negative 3 times negative 3 is negative 27. So if this index here is odd, then the amount inside, the radicand, can be positive or negative. I'm going very fast here, right? Because we've done all this before. Fifth root of 0 is 0. How about the 17th root of 0? 0. Any root of 0 is 0 because 0 times 0 times 0 times 0 as many times as you want still equals 0. Okay, we're going to look at domain and range here. So with square roots, you know that the amount inside a square root has to be positive or 0. In other words, the domain here, x has to be greater than or equal to 0. The range. So what are the possible answers you can get for y? Well, the smallest x number you can put in there is 0, and the square root of 0 is 0. So that's the smallest y value you can get. And then you can make x bigger and bigger and bigger and bigger, and the y gets bigger and bigger and bigger and bigger. So the range is y is greater than or equal to 0. Cube root of x. Domain, all reals. Doesn't matter what you put in there, right? If it's an odd index, you have a 3 here, it's an odd index, you can put any number you want into the x. Range, all reals as well. Because your x can be very, very big, and then you get very, very big y's for your answer, or your x can be very, very big negative, or small number if you want, and then the y's would be similar. Okay, fourth root of x squared. So what can x be in this case? You might think x has to be greater than or equal to 0, but look, you're squaring it. So that means x can be any number. Why? Because when you square the number, whether x is positive or negative, when you square it, you get a positive. So that's fine. How about y? Can't be all reals, because once you take the fourth root, since you have an even index, right, that 4 right there, since you have an even index, your answer is going to be greater than or equal to 0. Next one, x minus the square root of x minus 3. Well, this is an even index, right? There's a little invisible 2 right there. So that amount inside the x minus 3 has to be greater than or equal to 0. If you solve that by moving the 3 over, x is greater than or equal to 3. The range, well, again, if you're taking the root, the square root of something, the amount coming out has to be greater than or equal to 0. Okay, last one, a little bit tricky here. We have a 6th root. So it's even again. That means that the 5 minus 2x has to be greater than or equal to 0. Let's solve that. Subtract 5 from both sides, and then divide by negative 2. If we're dividing by a negative, when you have inequalities, the inequality flips over. So it's going to be x is less than or equal to 5 over 2. Now, if it didn't have this minus 2 here, if that wasn't there, so let me cross it off for a second. If that wasn't there, if this was just the question, then since this is an even index, our range would be y is greater than or equal to 0, because the smallest amount you can get is 0. But look at, you do have a minus 2. So that means the smallest amount you can get 0, take away another 2, so y is greater than or equal to negative 2. It's that vertical translation down 2, right? So that's another way you could think of it. All right, solve the following. Now, when we solve equations, we don't just consider the principal roots, we have to consider all the roots, because you're asking which number or numbers would work here. Okay, for the first one, you would take the cube root of 8, and there's only one number that works, it's 2. Next question, you take the cube root of negative 64. Does that work? Can you have a negative there? Yes, you can, because it's a cube root, so it's negative 4. Next one, you take the square root of negative 36. Does that work? No, it doesn't. Next one, and actually to be really precise, when you have an even index, you need to do plus minus. It doesn't really come into play here, but in this next example it certainly will. You take the square root of both sides, and you need to put plus minus. Why didn't you do that back here? Because this was an odd index. The index was 3, so no plus. So I don't know if we need to write this down, but odd index, no plus minus. But if you have an even index, you have to put plus minus in when you're solving equations. So our answer is x equals plus or minus 6. Right? Makes sense? Positive 6 squared is 36. Negative 6 squared is 36. Why do we not put plus or minus 2 here? Because, just let me erase this. We didn't put plus or minus 2 here because positive 2 cubed is 8, but negative 2 cubed is how much? Negative 2 cubed is negative 8. So that's why you can't put plus minus in those ones. Okay, last one. X equals the fourth root of 32. Oh, it's an even index, so I need to put plus minus. Sorry about the mess there. That says x equals plus minus the fourth root of 32. You could simplify the fourth root of 32 by doing your tree. 16 times 2, 8 times 2, 4 times 2, 2 times 2. Because the index is 4, we need a group of 4. There it is. So that comes out front, the 2, plus or minus 2. And what's left is the fourth root of, there's 1 2 left over. Good. It's not 2 plus or minus the fourth root of 2. It's plus or minus 2 times the fourth root of 2. Okay, simplify the following. This one, you take the square root of 49, it's 7. Take the square root of m to the fourth. Well, that's like m times m times m times m, and since the index is 2, you need 2 to bring them out, so you can bring out 2. You get 7m squared. Next one, square root of 49 is 7. This is like m times m. You need 2 to bring it out, so you get 7m. Guess what? There's one last thing you have to do in this question. You're going to hate this. You know what you have to do? You have to put absolute value signs around the m. Why is that? And why didn't we do that here? Okay, let's see if I can explain this without taking too much time. Pretend m is negative. M is negative. First of all, if m's positive, it doesn't make any difference whether we put absolute value signs, but we don't know if m's positive or negative, right? We don't know. But if m was positive, it'd be fine, because to fourth power, positive, squared is positive, and then multiplying by 49 is still positive, and the square root is positive, and 7m, everything's positive. It's no big deal. But take a look when m is negative. If m is negative, a negative to the fourth power is positive, 49 times a positive is a positive, and the square root must be a positive amount. So this amount right here has to be positive. Is it? Yeah, for sure, because whether m is positive or negative, when we square it, we get a positive amount. So this amount has to be positive, and in this case, it definitely is. Now, consider this case. Pretend m is negative again. M squared, so it's a negative squared, is a positive, and a positive times 49 is still positive, so it's good. We can take the square root of this amount. But when we take the square root of something, we have to get a positive amount. This amount has to be positive. If we didn't put absolute value signs on this, we'd have 7 times m, and m is negative. 7 times a negative is negative. That doesn't make sense. So you have to put the absolute value signs to show it's 7 times the positive m. Even if m's negative, you're making it positive. Okay? We did that before and many of you hated it, and you probably don't like it anymore this time. Cube root of 64 m to the 6. Cube root of 64 is m. Sorry, the cube root of 64 is 4, and then we have 6 m's, 1, 2, 3, 4, 5, 6, and we need to have 3, and so you get m squared. By now you've probably realized all you need to do to figure out the exponent here is divide. 6 divided by 3 is 2. 2 divided by 2 is 1. 4 divided by 2 is 2. With that in mind, the cube root of 64 is 4. 3 divided by 3 is m. Do I need to put absolute values here? No. Why not? Because this is an odd index. With an odd index, you never have to worry about that. We love odd indices. You don't have to do any thinking. Odd indices, you don't have to do any thinking. Cube root of negative 64 is negative 4. Cube root of m cubed is m. I'm finished. Moving on. Last thing we're going to look at today is comparing the graphs of a function and then the square root of a function. I don't know the best way to do this, so maybe what I'll do is I'll show you the points I want to make. I'll let you write them down, and then I'll draw these graphs and I'll show you what these points mean. So write down the 4 points and meet me back here. Okay, hope you got that down. If not, go back and pause the video. Don't try to write it all down without putting pause. We are going to graph y equals x and y equals the square root of x. So y equals x should be no problem. We have drawn that for years and years. It is a line that is in a 45-degree angle from there to there, right? The slope is 1 over 1, and the y-intercept is 0. So this is what that is. This is y equals x. The domain of this, well, x can be anything. It's all reals. Now, if we graph this is actually a mother function for square root, so hopefully you remember this. It goes to the point 0, 0, it goes to the point 1, 1, it goes to the point 4, 2, and it goes to the point 9, 3. If I graph that, I'm going to exaggerate this a little bit. My exaggeration's over here, and I'll show you why in a second here. Okay, now let's take a look at some. Oh, what's the domain here? The domain of this graph is x is greater than or equal to 0, right? You can't put a negative number in there. So what are these points saying? The first point says if 0 and 1 are in the range of the original function, well, they definitely are. There are points that have a y value of 0. It's that point right there. Maybe I'll do it in a different color. This point right here on the black line has a y value of 0, and this point right here on the black line has a y value of 1. And what it's saying is those points are going to be on both graphs, so that point's also going to show up on this graph, and it did, didn't it? Why is that? Because if you have a amount that's equal to 0, and then you take the square root of that 0, square root of 0 is 0, it stays the same. And if you have an amount that equals 1, the square root of that amount is still 1. So those 2 points stay the same. Second point, where the graph of y equals fx is above the x-axis but below at y equals 1, the graph of, I hate this. This sign should go all the way over, this sign should go all the way over, this sign should go all the way over. The graph of the square root of y, the graph of the square root of fx is above y equals fx. What are we saying there? We're saying that between where y equals 0, so that's this line here, the x-intercept, and where y equals 1, in between that area, the square root function should be higher than the function. And that's, in this case, it's true. I know I've kind of exaggerated a little bit, but that's why I exaggerate. I wanted you to see that. The red one is above the the black one. But then, once you get above this 1, the black one should be on top of the red one. That's what this says. Where the graph is above y equals 1, the graph of y equals the square root of fx, that's the red one, is below y equals fx. Remember that this is y equals the square root of x here. And the last thing it says is, well, just let me show you. So this is y equals the square root of x. Just let me prove that to you by doing an xy table with just 1 point in it. Let's put 0.5 in there. In this graph, the black one, if you put 0.5 in, you get 0.5. But in the red one here, when you take the square root, if you put 0.5 in, You get the square root of 0.5, and I have a calculator in front of me. I'm doing this right now. You can trust me with this. I won't make up the answer. The answer is 0.7. So you see that the red one at 0.5, the red one is actually on top of the black one. But once you get beyond 1, the black one's always above the red one. Okay, the last point here is where the graph of y equals fx is below the x-axis. So that is for all these points down here. All these points are below the x-axis. The graph of the square root of fx does not exist. There's no, right? There's no points for the graph. Why is that? Because all these points are negative. You can't have you can't take the square root of a negative amount. So those ones just do not exist at all. Okay, we'll do a couple more, and I think you'll get this. So the next one I want to do is y equals x squared, and y equals the square root of x squared. All right, we've done y equals x squared a whole bunch of times. Looks like this. What is the domain of that? All reals. Now, let's graph this one, the square root of x squared. This is kind of interesting, actually. If we do an xy table for this, because we've never graphed this before, let's fill it in. Negative 3 squared is 9, and the square root of 9 is 3. Negative 2 squared is 4, and the square root of 4 is 2. Oh, negative 1 squared is 1, squared root is 1, 0. 1 squared is 1, and the square root of 1. Do you see what's happening? Basically, when you square and take the absolute value, it's like taking when you square and take the square root, it's like taking the absolute value. This is exactly the same as the absolute value graph. Why would that be? Because if we were to simplify this, like we did at the bottom of the last page, we would say that the square root of x squared equals x, but because we have an even index here, and we don't know whether x is positive or negative, you would need to put absolute value. This is exactly the same thing. It's the same graph here. So we would expect it to look exactly the same as the absolute value graph, and it does. The way it looks is absolute value graph goes like this and goes like this. Now, again, it's hard to graph these on such a small graph, but what you should see is that at the point 0, wherever y equals 0 on the black one, it's the same, yes. Wherever y equals 1, well, that's here and here. They should share that point. They do. You should see that between 0 and 1, the red one's on top. You can definitely see that on this side. It doesn't look like it on the left side, but it is, believe me. And then once you get beyond y equals 1, so it's all these points up here, the black one's definitely above the red one. Again, if you don't believe me with that red one being on top here, try his points. Try xy again for 0.5. If you put 0.5 in here, 0.5 times 0.5 is 0.25. But if you put it into this one, 0.5 squared and the square root of it is 0.5. Yep, 0.5 is higher than 0.25. So the red one should be higher in this little section down there, and the black one's higher up there. And the last point is that wherever the original one, the black one's below the x-axis, well, it's never below the x-axis, so that point doesn't come into play. Okay, the domain of this one, well, it looks like x can be anything, so x is all real. Okay, there's a y sitting there for some reason. Let's use it. Let's draw the graph of y equals x cubed and y equals the square root of x cubed. X cubed is another mother function, goes through 0, 0, 1, 1, and 2, 8. Also goes through negative 1, negative 1, and negative 2, negative 8. So it looks something like this. What's the domain of that? All reals. Now we want to do this graph here. So let's try to use our things we've been learning about, the points up above. Wherever the y value is 0, that's right here, or 1, that's right here, the points will be the same. So we know our graph of this is going to go through those 2 points. Where it's between 0 and 1, so between this area, the red one should be on top, so it should go something like, I don't know, something like that. It's on top. Now, I don't know what it's going to do after that. Is it going to come out here? Is it going to go up there? So let's make a little table. Wow, that's terrible. Let's try some points. Let's try well, we know what happens at 1. It goes through 1, 1. Let's try 2, 3, and 4. 4 is a beauty, because 4 cubed is 64, and the square root of 64 is 8. 3 cubed is 27, and the square root of 27 is something like 5.2 or something. So let's graph these. 4, 8, square root of 27, I don't know exactly. It's about 5 point something. So 3 and 5 point something low. And 2 cubed is 8, and the square root of 8 is just below 3. So 2 and just below 3, like that. So it's going to come like that. Okay, and the last one we'll do, oh, what's the domain of this last one that we just did here? The domain is x is greater than or equal to 0. A point I didn't make is that for all these points down here, they're all below 0. They're all negative values. So we don't have to worry about those points. It doesn't exist for the square root function. Okay, last one. Y equals negative 2x squared plus 8, and then y equals the square root of negative 2x squared plus 8. So this is a vertex at 0, 8, and it faces down, and the step pattern would go over 1, down 2, over 1, down 6, over 1, down 10. So down 2, down 6, down 10. Good luck to me drawing this. Yeah, not too bad. And all right, good enough. So that's this one here. What's the domain of that? All reals. Now we want to graph the square root of that function. So again, all the points down here which are below 0 and all the points down here which are below 0, you don't have to worry about all those points. You can't take the square root of a negative. Points that are at 0, like a y value of 0, are going to be the same. Points that are at 1 are going to be the same. Between those, the red one should be on top, so it's going to be something like that, I guess, and that. I don't know. The red one's supposed to be higher. It's very hard in this small graph. And then we probably need to do a table to get some extra points. We need to know what's going to happen for values like negative 1, 0, and 1. So plug it in. Negative 1 squared is 1 times negative 2 is negative 2 plus 8 is 6, and then we have to take the square root. So square root is 6. That's going to be the same for the bottom one because 1 squared is also 1 times negative 2, blah, blah, blah. So it's square root of 6. And if you put 0 in there, you get 8 and then the square root of 8. So we need to know what these are about. Square root of 6 is around 2.4, and the square root of 8 is around 2.8. So we'll graph that. Negative 1, 2.4, 0, 2.8, back down to 2.4. So it comes up, makes a nice half parabola sort of thing. That's the graph there for the square root of negative 2x squared plus 8. What's the domain there? Well, interesting. The domain's from negative 2 less than or equal to y less than or equal to 2. It's between negative 2 and 2, isn't it? Okay, there you go. The only thing I didn't do that they talk about in this chapter is transformations of square root graphs, but we did that in the transformation chapter, chapter 1. So if you don't remember how to do that, you could review chapter 1 a little bit.